I told you when we last met a good deal about carbon dioxide. We found by the lime water test that when the vapor from the top of the candle was received into bottles and tested by a solution of lime water, the composition of which I explained to you and which you can make for yourselves, we had that the white opacity, which was in fact calcareous matter like shells and corals and many of the rocks and minerals in the earth. But I had not yet told you fully and clearly the chemical history of this substance, carbon dioxide, as we have it from the candle, and I must now resume that subject. We have seen the products and the nature of them as they issue from the candle. We have traced the water to its elements, and now we have to see where are the elements of the carbon dioxide supplied by the candle. A few experiments will show you this. You remember that when a candle burns badly, it produces smoke. But if it is burning well, there is no smoke. And you know that the brightness of the candle is due to the smoke, which becomes ignited. Here is an experiment to prove this. So long as the smoke remains in the flame of the candle and becomes ignited, it gives a beautiful light and never appears to us in the form of black particles. I will light some fuel, which is extravagant in its burning. This will serve our purpose, a little lighter fluid on a sponge. You see the smoke rising from it and floating into the air in large quantities. And remember now, the carbon dioxide that we have from the candle is from such smoke as that. To make that evident to you, I will introduce this into a container where I have plenty of oxygen, the rich part of the atmosphere. You now see that the smoke is all consumed. The carbon which you saw flying off from the lighter fluid flame in the air is now entirely burned in this oxygen, exactly as in the combustion of the candle. All the carbon which is burned in oxygen or air comes out as carbon dioxide, while those particles which are not so burned show you the second substance in the carbon dioxide, namely the carbon, that body which made the flame so bright while there was plenty of air, but which was thrown off in excess when there was not oxygen enough to burn it. There is another experiment which I must give you before you are fully acquainted with the general nature of carbon dioxide. Being a compound body consisting of carbon and oxygen, carbon dioxide is a body that we ought to be able to take asunder, and so we can. As we did with water, so we can with carbon dioxide, take the two parts asunder. The simplest and quickest way is to act upon the carbon dioxide by a substance that can attract the oxygen from it and leave the carbon behind. You recollect that I took potassium and put it upon water or ice, and you saw that it could take the oxygen from the hydrogen. Now, suppose we do something of the same kind here with this carbon dioxide. Now, let me take some magnesium turnings and get them to act upon carbon dioxide in the form of dry ice. If we apply heat to the magnesium, you will see that it can burn in carbon dioxide, and its very burning is proof of the existence of oxygen in the carbon dioxide. In addition to a brilliant light, you will see what is left behind. we find that besides the white powder formed, which is magnesium oxide, there's a quantity of carbon produced, carbon obtained from the carbon dioxide as a common black substance, so that you have the entire proof of the nature of carbon dioxide as consisting of carbon and oxygen. And now, I may tell you that whenever carbon burns under common circumstances, it produces carbon dioxide. Suppose I take this piece of wood and put it in a bottle with lime water. I might shake that water up with wood and the atmosphere as long as I pleased. It would still remain clear as you see it. But suppose I burn the piece of wood in the air of that bottle. You, of course, know that I get water. Do I get carbon dioxide? There it is, the carbonate lime which results from carbon dioxide, and that carbon dioxide must be formed from the carbon which comes from the wood, from the candle, or any other thing. Indeed, you have yourselves tried a very pretty experiment by which you see the carbon in wood. If you take a piece of wood and partly burn it and then blow it out, you have carbon left. Here is the piece of wood that I partly burnt. You see the carbon left on it. A candle does not show it, nor does a Bunsen burner, but both contain carbon. You see no carbon when they burn, but you see a flame, and because it is bright, it will lead you to guess that there's carbon in the flame. I hope that by these experiments you will learn to see when carbon is present and understand what are the products of combustion when gas or other bodies are thoroughly burned in the air. Before we leave the subject of carbon, let us make a few experiments and remarks upon its wonderful condition as respects ordinary combustion. I have shown you that the carbon in burning burns only as a solid body, and yet you'll perceive that after it is burned, it ceases to be a solid. There are very few fuels that act like this. It is in fact only that great source of fuel, the carbonaceous series, the coals, charcoals, and woods that can do it. I do not know that there is any other elementary substance besides carbon that burns with these conditions. And if it had been so, what would happen to us? Suppose all fuel had been like iron, which, when it burns, burns into a solid substance. We could not then have such a combustion as you have in a fireplace. Now, I must take you to a very interesting part of our subject, to the relation between the combustion of a candle and that living kind of combustion which goes on within us. In every one of us, there's a living process of combustion going on very similar to that of a candle. And I must try to make that plain to you. For it is not merely true in a poetical sense, the relation of the life of humans to a candle, and if you follow, I think I can make this clear. In order to make the relation very plain, I've devised a little apparatus with an air inlet at the bottom, and I'll limit the airflow out of the top with this wire mesh. The lighted candle goes on, you see, burning very well. You observe that the air which feeds the flame goes along the horizontal tube and ascends the vessel. If I stop the aperture through which the air flows, I stop combustion, as you will perceive. I stop the supply of air, and consequently the candle goes out. But now, what will you think of this fact? In a former experiment, I showed you the gaseous products coming from one burning candle to a flame. If I take the vapor proceeding from another candle and send it through this tube, I should put this burning candle out. But what will you say when I tell you that my breath will put out that candle? I do not mean by blowing it out, but simply that the nature of my breath is such that a candle cannot burn in it. I will exhale, and without blowing the flame in any way, let no air enter the tube but what comes from my mouth. You see the result. I did not blow the candle out. I merely let the air which I expired pass into the aperture, and the result was that the light went out for want of oxygen and for no other reason. My lungs had taken the oxygen out of the air, and there was no more to supply the combustion of the candle. It is, I think, very pretty to see the time it takes before the bad air which I throw into this part of the apparatus has reached the candle. The candle at first goes on burning, but so soon as the air has had time to reach it, it goes out. To pursue this a little further, let us see what will happen with lime water. Here is a flask which contains a little lime water and is so arranged as regard the pipes as to give access to the air within so that we can ascertain the effect of respired or unrespired air upon it. Of course, I can either draw air in here and so make the air that feeds my lungs go through the lime water, or I can force the air out of my lungs through this tube which goes to the bottom and so shows its effect upon the lime water. You will observe that, however long I draw the external air into the lime water and then through it to my lungs, I shall produce no effect upon the water. It does not make the lime water turbid, but if I throw the air from my lungs through the lime water several times in succession, you will see how white and milky the water is getting, showing the effect which expired air has upon it. And now you begin to know that the atmosphere, which we have spoiled by respiration, is spoiled by carbon dioxide, and you see it here in contact with the lime water. Let us now go a little further. What is all this process going on within us which we cannot do without, either day or night? If we restrain our respiration, as we can to a certain extent, we should destroy ourselves. When we are asleep, the organs of respiration and the parts that are associated with them still go on with their action. So necessary is this process of respiration to us, this contact of the air with the lungs. I must tell you, in the briefest possible manner, what this process is. We consume food. The food goes through that strange set of vessels and organs within us and is brought into various parts of the body, into the digestive parts especially. The air that we inhale is drawn into the lungs, absorbed into the bloodstream, and transported throughout the body so that the oxygen and the food come close together. In the body, a curious, wonderful change takes place. The oxygen combines with the carbon, not carbon in a free state, but is in this case placed ready for action at the moment, and makes carbon dioxide, and is so thrown out into the atmosphere, and thus the singular result takes place. The oxygen can thus act upon the food, producing precisely the same results in kind as we have seen in the case of the candle. The candle combines with parts of the air, forming carbon dioxide, and evolves heat. We may thus look upon the food as fuel. Let us consider sugar, which will serve my purpose. It is a compound of carbon, hydrogen, and oxygen, similar to a candle, as containing the same elements, although not in the same proportion, the proportions being as shown in this table. This is indeed a very curious thing which you can well remember, for the oxygen and hydrogen are in exactly the proportions which form water, so that sugar may be said to be compounded of 72 parts of carbon and 99 parts of water. And it is the carbon in the sugar that combines with the oxygen carried in the air by the process of respiration, so making us like candles, producing these actions, warmth, and far more wonderful results besides, for the sustenance of the system by a most beautiful and simple process. To make this still more striking, let me show you an experiment with a bit of sugar. If I put some sulfuric acid on sugar, it takes away the water and leaves the carbon in a black mass. You see how the carbon is coming out, and before long we shall have a solid mass of charcoal, all of which has come out of the sugar. Sugar, as you know, is food, and here we have absolutely a solid lump of carbon where you would not have expected it. Recall that I oxidized sugar in an earlier lecture using potassium chloride, which is a quicker one than the atmosphere, and different from respiration in its form, though not different in its kind. What occurs in my lungs, taking in oxygen from another source, namely the atmosphere, takes place between potassium chlorite and sugar by a more rapid process. I also showed you how potassium reacted with water. The moment the potassium was brought to the water, it acted. But a beautiful instance of chemical affinity by which all our operations proceed. When we breathe, the same operation is going on within us. When we burn a candle, the attraction of the different parts one to the other is going on. We have this difference between charcoal and potassium that, well, the potassium can start into action at once. If there be access of water to it, the carbon will remain days, weeks, months, or years in the presence of air. The manuscripts of Herculaneum were written with carbonaceous ink, and there they have been for almost 2,000 years, not having been at all changed by the atmosphere, though coming in contact with it under various circumstances. Now, what is the circumstance which makes the potassium and carbon differ in this respect? It is a striking thing to see that the matter which is appointed to serve the purpose of fuel waits in its action. It does not start off burning like the potassium. The carbon waits for action. This waiting is a curious and wonderful thing. Candles do not start into action at once like the potassium, but there they wait for years, perhaps for ages, without undergoing any alteration. It is curious to see how different substances wait, how some will wait till the temperature is raised a little, and others till it is raised a good deal. I have here a little gunpowder and some gun cotton. Even these things differ in the conditions under which they will burn. The gunpowder is composed of carbon and other substances, making it highly combustible, and the gun cotton is another combustible preparation. They are both waiting, but they will start into activity at different degrees of heat or under different conditions. By applying a heated glass rod to them, we shall see which will start first. You see the gun cotton has gone off, but not even the hottest part of the rod is now hot enough to fire the gunpowder. How beautifully that shows you the differences in the degree in which bodies act in this way. In the one case, the substances will wait any time until the associated bodies are made active by heat, but in the other, as in the process of respiration, it waits no time. The air that enters when we breathe unites with the carbon. Even in the lowest temperatures which the body can bear short of being frozen, the action begins at once, producing the carbon dioxide of respiration, and so all things go on fitly and properly. You will be astonished when I tell you what this curious play of carbon amounts to. A candle will burn some 4, 5, 6, or 7 hours. What then must be the daily amount of carbon going up into the air in the way of carbon dioxide? What a quantity of carbon must go from each of us in respiration. What a wonderful change of carbon must take place under these circumstances of combustion or respiration. A person in 24 hours converts as much as 200 grams of carbon into carbon dioxide. A dairy cow will convert 2,000 grams and a horse 2,200 solely by the act of respiration. That is, the horse in 24 hours burns 2,200 grams of charcoal or carbon in his organs of respiration to supply his natural warmth in that time. All the warm-blooded animals get their warmth in this way, by the conversion of carbon, not in a free state, but in a state of combination. And what an extraordinary notion this gives us of the alterations going on in our atmosphere. As much as 1.5 million tons of carbon dioxide is formed by human respiration in the world in 24 hours. And where does all this go? Up into the air. If the carbon had been like iron, which in burning produces a solid substance, what would happen? Combustion could not go on. As charcoal burns, it becomes a vapor and passes off into the atmosphere, which is the great vehicle, the great carrier for conveying it away to other places. Then what becomes of it? Wonderful it is to find the change produced by respiration, which seems so injurious to us, for we cannot breathe air twice over, is the very life and support of plants and vegetables that grow upon the surface of the earth. It is the same also under the surface, in the great bodies of water. For fishes and other animals respire upon the same principle, though not exactly by contact with the open air. Fish respire by the oxygen which is dissolved from the air by the water and form carbon dioxide. And they all move about to produce the one great work of making the animal and vegetable kingdom subservient to each other. And all the plants growing upon the surface of the earth absorb carbon. These leaves are taking up their carbon from the atmosphere, to which we have given it in the form of carbon dioxide, and they are growing and prospering. Give them a pure air like ours, and they could not live in it. Give them carbon with other matter, and they live and rejoice. This tree, as do all plants, gets its carbon from the atmosphere, which, as we have seen, carries away what is bad for us and at the same time good for them. What is disease to the one, being health to the other. So are we made dependent not merely upon our fellow creatures, but upon our fellow existers, all nature being tied together by the laws that make one part conduce to the good of another. Indeed, all I can say to you at the end of these lectures, for we must come to an end at one time or other, is to express a wish that you may, in your generation, be fit to compare to a candle, that you may, like it, shine as lights to those about you, that in all your actions you may justify the beauty of the taper by making your deeds honorable and effectual in the discharge of your duty to humankind.